Okay, we're going to talk about trig functions. Yesterday, you guys had to talk about sine, cosine, tangent, and just get a feel for what the graphs look like. And you answered a couple questions just interpreting the graphs. But now we have to go a little deeper with the sine, cosine, and tangent. And then we'll talk about the reciprocals. But first, we'll just start with the basic fundamentals, right? So right here on Desmos, we have our sine of x graph. If you notice, I made it so the x-axis increases by pi over 2s. So you can kind of see how the graph progresses. And this is something called an oscillating function because if you think about the word oscillate, it means to bounce essentially back and forth between two parts. So that's what this is. Another way we can call this is a sinusoidal because it has such a special behavior where it kind of goes up, down, up, down, up, down, and it just keeps going like that forever and ever. If you want to, you can go to Desmos and play with this graph yourself and sort of see what you notice. But I want to give you some basic tips. Or, not tips, facts. When it comes to the sine graph, here's what I know. The domain is all real numbers. I could put any number I want in for x in the sine of x graph, and it will spit out some value. However, for the base function of the sine of f graph, when we talk about the range, right, kind of a throwback to our first unit, the outputs of sine oscillate between -1 and 1, right? So it just keeps oscillating between those two values forever and ever. You should know that we have the coordinate point 0, 0 right there as our y-intercept, and also one of the several infinite x-intercepts this graph could have. So here's what I want to do. I also want to point out something called the period of the graph. So like I said, these graphs tend to oscillate forever and ever and ever, repeating the same behavior. So what the period is it tells me the span of quote-unquote time. How often does this graph oscillate? So I start at 0 and I go all the way to 2 pi, and in that I start at 0, 0, go up, then come down, then go back up to 0, 0, and I kind of start going back up again. If I look backwards, right, I would say the period for a typical sine graph is 2 pi. Right? Every single 2 pi, this graph is going to repeat. So notice here it starts there, it goes up, then it equals 0, then it bottoms out, then it comes back to 0, and that same kind of, let's call it a unit, repeats itself. And it'll keep doing this forever and ever based off the graph. So those are some of the basic facts you should know about the sine graph. So, aside from that, going back to what we knew about the first unit, the first unit was dealing with the transformations of functions, and we very briefly kind of threw the idea of sine and cosine graphs at you without much explanation for how they worked or where they came from. But now you have that, right? So, with that said, if I keep this as my basic piece of information, like these are the facts that occur for a typical sine graph, where it's just sine of x, what you would want to think about is what happens with the a, the b, and the c value that I've kind of put up there, right? These are talking about all the different transformations possible. Got a, you got, B, you got C, and you got, yeah, all right, let's go blue for D. All those change this graph. So what I would recommend is, as I go through my slider, take a note as to what aspect of the graph is changing. Is the domain changing? Is the range changing? Is the y-intercept changing? Is the period changing? Okay, how often the graph oscillates. Okay, so let's start with the A. Now I'll get rid of the marker. Okay, so if I start this, it would help if you could actually see the graph. So let's back it up. All right. A is 0 means that I'm multiplying this sine function by a 0. So that makes sense. And actually, let's set these all equal to 0. Hopefully that doesn't change. Actually, no, I'm going to be strategic. The B I need to set equal to 1. The C needs to be 0. And the D value needs to be 0. Right? If I change A equal to 1, notice how it overlaps perfectly with the sine graph. So that means that that's what a basic sine graph looks like. However, if I change A, notice what's happening with the graph. And actually, let's do something better. Let's just change it so that it goes from 0 to a 10. Because if I include negative values, remember that does negative values that multiply are reflections over the x-axis. And so we're just going to keep that separate from now, and we'll deal with it when time comes, all right? So notice, if I just change the A value, think about what aspects of the graph is changing, right? If I leave it here at 5, what would the new domain be? What would the new range be? What would the new y-intercept be? What would the new period be, right? If you notice, there are some points that aren't changing. The x-intercepts still happen to be the same at 0, 0, pi comma 0, and 2 comma 0, right? And if I kind of keep toggling through, those points don't change when I change the A value, right? They're still right there, they're still right there, and they're still right there. That doesn't change. So let's go back and let's reset A to equal 1 so we get back to the parent function. If you remember what the B does, you'll remember that I was very adamant about what would constitute a horizontal stretch versus horizontal stretch or shrink versus a vertical stretch or shrink. And this is why I was very particular about it, because I knew we would eventually come to this road. Notice what's happening to the graph as the B value gets larger, right? And what's happening as I get closer and closer and closer to 0. 0, it flattens out, and then it gets all weird. So we're going to ignore the negatives because, again, the negatives mean that you're going to reflect over an axis. In this instance, when you have a negative B value, it reflects over the y-axis, so it switches out. Notice how you have a maximum here at pi over 2 divided pi over 2 comma 1, and now that changes to a negative pi over 2 comma 1. That's what the negative would do, right? So let's reset and let B equal 1. We let A equal 1, so we're back to the parent value. Let's talk about what C does, if it will play. Any second now. a little trippy, but think about going back to our transformations unit. What did that value that was directly next to the x inside the parent function do to the graph? How did it transform it? Because that's a transformation that we're seeing here, right? Now it looks like the graph is moving left to right. So just be careful with how that works and think about what would that do to the domain, if anything at all. So we'll reset it back to 0. Now let's take a look at the d value. All right. So if I change the d value and let it go, going back to our transformations unit, what does that actually do to our graph of sine? So just keep that in mind. Think about which of these aspects changes. The period changes, the does the range change, the domain changes, the y-intercept change, okay? And I figure we can do this kind of a 2-for-1 deal. So give me 1 sec. Okay, so we have the sine graph back up. So now let's talk about the cosine graph. So I'm going to put them both up on the same screen so you can kind of see them. And hopefully you can tell how are they similar, how are they different. So if you look at the graphs, take a minute, I would say pause the video and just look at them. What do they both have in common? What's different? So one thing I would note is this. These are kind of the same deal, except they behave a little differently. So this one, the cosine graph, has a y-intercept down there or up there at 1, 0. All right. So let's see if the period is still the same in terms of 2 pi. So I'm going to go ahead and get rid of the sine graph because we don't need that anymore. If I take a look at the cosine graph, here's what I notice. It starts at this maximum value here and goes down, then goes up. Then it reaches another maximum over here, right? Over here's another maximum. Okay, so now let's trace along. It starts at the maximum, it goes down, bottoms out, then it starts to increase, maxes out, then it starts to decrease, bottoms out, then starts to increase, maxes out. So notice, it starts on a high note and it ends on a high note. Starts on a high note, ends on a high note. That's what one cycle for the cosine graph looks like, right? And it bottoms out halfway between the two maximums. So the period of 2 pi still stays the same. I would say that given that sine and cosine, like the graphs kind of look similar, I would say that everything I said about sine, for the most part, would be true. Later on, I'll explain what even and odd functions are, because that's a major difference between sine and cosine. And I'll explain something called phase shift, but for now, remember back to your first unit. Vertical stretch or compress, horizontal stretch or compress, moving left or right, going up or down. Think about how A, B, C, and D can transform and what that would look like in a graph. Then we'll talk about tangent.